Let's get started. We're going to finish carbohydrate analysis today and start fat characterization, which is the subject of next week's lab. So with carbohydrate analysis, we covered starch analysis last time, and we also talked about utilizing enzymes for the analysis of carbohydrates. So can you briefly tell me what's the basis of carbohydrate analysis using enzymes? So what is the basis of the use of enzymes in the analysis of carbohydrate? Very simple basis. Anybody? I don't like to look at these folks here because there's so few of them, and they feel that I might be pressuring them. So go on, type in something. Nobody's going to give me a basis? Come on. What do we do? Enzymes, Dan? Yes. Well, thank you, Dan, for being so brave to talk about these reactions. So coupled reactions sometimes is what we need, a coupled reaction, which is auxiliary, the measuring reaction, and then the indicator reaction. But sometimes we don't need the coupling reaction. Sometimes it's just one reaction. But the idea is when you use enzyme, you have a substrate, and your substrate is the carbohydrate of interest. You want to generate a chromophore that we can measure absorption. So the basis of the analysis with an enzyme is to measure a constituent that serves as a substrate to the enzyme, providing a product that can be measured spectrophotometrically. So that means a product that has a chromophore. And yes, to Dan's point, sometimes we need to do coupled reaction, sometimes just one reaction. The coupled reaction would be the first reaction did not give me a product that is a chromophore, but can be reacted with another component to give me a product that I can measure that is a chromophore. Okay, so can you remember some of the enzymes involved in starch analysis? So if you have starch and we need to use an enzyme reaction, starch is a big molecule. So the first thing you want to do is what? Conversion of starch to glucose. Exactly. That's the first step that you want to do. When you're measuring total starch or amylose or amylopectin, we want to convert our starch molecule into glucose. So what we use to convert starch into glucose is alpha amylase and glucoamylase. So the alpha amylase is an endoenzyme, so it's going to chop up my starch into maltodextrins or small chains of glucosides, and then amylo or glucoamylase is an exoenzyme that's going to take one glucose unit at a time out of my starch molecule. So then we end up with a glucose, and then we have a coupled reaction for glucose to measure the amount of total glucose, because glucose is still not a chromophore. Then we have to use peroxidase enzyme. And okay, so let's look at the reaction. So first of all, we use glucose oxidase to generate peroxide, and then we use peroxidase to oxidize a dye. So we get the peroxidase helping the peroxide oxidize a dye to give you an oxidized dye that you can measure using a spectrophotometer. Okay, so this is the coupled reaction. So when I ask you in an exam, what are the enzymes involved in total starch analysis? So the correct answer would be all four of the enzymes: the alpha amylase, the glucoamylase, the glucose oxidase, and peroxidase. Okay, so all of these enzymes are involved in the analysis of total starch. So first set of enzymes are involved in the breaking of starch to glucose units. And the second set of enzymes is used for the actual detection of glucose. All right, good. So what are the enzymes involved in starch analysis? We covered that. So I only had two questions today. Only had two questions. Moving on. All right, so what we have next is measuring degree of gelatinization and degree of retrogradation. So remember at the beginning of the carbohydrate section, I asked this question of can we use the same method for measuring both degree of gelatinization and degree of retrogradation? And the answer is yes. So in this case, we use the two enzymes that do not act on raw starch and retrograded starch. They only act on gelatinized starch. So if we have a product and we want to determine the degree of gelatinization, we can use polynase and beta amylase. So in this case, polynase is going to debranch the starch, and beta amylase is going to cleave off 2 glucose units at a time, 2 or 3 glucose units at a time, giving us maltoses and maltotrioses. These are reducing sugars. We take these and use one of the reducing sugars methods, such as Smogy-Nelson, to determine total reducing sugar, total amount of reducing sugar. The higher amount of total reducing sugar, that means you have higher degree of gelatinization. If we want to measure degree of retrogradation, we use the same method. And the lower amount of reducing sugar indicates a higher degree of retrogradation. We always use references in these methods, a fully retrograded starch and a fully gelatinized starch as a basis for us to determine degree of gelatinization and degree of retrogradation. So therefore, one method can be used for both, but the outcome is opposite. Okay. Just checking if there is any question in the chat. All right, so we're moving on to fiber, dietary fiber. So far we talked about monodiglycosaccharides and starch analysis, and now we're going to talk about dietary fiber analysis. Just a brief review of a dietary fiber. So these plant components that are non-digestible. So they can be carbohydrate or carbohydrate plus lignin. So they are polysaccharides, oligosaccharides, and lignin. Lignin is not a carbohydrate, but it is a plant material that is non-digestible, thus it belongs to the dietary fiber component. We have soluble fiber and we have insoluble fiber. Soluble fiber is pectin, is your soluble fiber, also hydrocolloids and gums. So hydrocolloids such as beta-glucan, arabinoxylans, but some of them can be insoluble too. So not all of them are soluble. And hemicellulose can sometimes split between soluble and insoluble. It really depends on the branching and how big these are. But mostly pectin and hydrocolloids are soluble, and mostly cellulose, hemicellulose, and lignin and resistant starch are your insoluble. So there are different components, and it's so hard to be able to analyze all of them accurately following one particular approach. And we'll see how and why. So in the past, they used to analyze fiber using crude fiber method of analysis. But later on, the methods evolved to be able to determine dietary fiber content, because crude fiber content exclude pectin, and it can exclude hydrocolloids and also sometimes hemicellulose. So in most cases, crude fiber is mostly estimating cellulose, sometimes hemicellulose and lignin. So mostly cellulose and lignin. And that's not the entire uh, or the whole components of dietary fiber. So now crude fiber methods are no longer used for human food analysis. They are still used for feed analysis of fiber, but no longer for human. So for human food analysis, dietary fiber methods are used specifically. So the crude fiber, they are based on, you won't find them anymore listed, these methods in your book chapter because they just got rid of them because it's food analysis textbook. But I like to keep them here, especially I keep getting a questions from our agronomy collaborators and um, collaborators in the agriculture domain, and they keep asking us for crude fiber analysis. And I try to always remind them crude fiber is done for animal feed, is not done for human feed. So I'd like to always keep that here so that you also know if you ever have this conversation to know that the crude fiber method should not be used for food intended for human consumption. So the crude fiber analysis methods, you can either use acid digestion or alkaline digestion. So what you do is you have your food product or food sample, you add to it either acid or alkaline, and you heat and use a reflux system so that you can have a distillation, and you use the reagent or the to use the reagents efficiently and not have it boil off. So you reflex the sample, everything gets digested except your cellulose and lignin. So these will precipitate, you can remove the supernatant, and you can quantitate the cellulose and lignin. But again, there are no hemicellulose, no pectins, no hydrocolloids, they're all going to be hydrolyzed. Same with detergent extraction. So using a detergent, you can do the same extraction, and but the similar to the other one, you are measuring cellulose, lignin, and some hemicelluloses. So anyway, not no longer used for us for food analysis. The methods that are used are dietary fiber approved methods of analysis, which are your AOAC methods of analysis. So it's very tedious. Ask my group members, lab group members. They don't like measuring dietary fiber. Rachel is shaking her head. I said, I'm only going to talk about the dietary fiber, not the integrated. The integrated is even worse, right? So why is it nobody likes it? Because it's very involved and lengthy. What you do is you get your sample that is hopefully dry. So if it's not dry sample, you pre-dry it. If it has a high fat content, you defat it. If fat content is 2% or less, that's fine, you continue with it. So you pre-dry, you defat your sample, and then you want to break down everything except dietary fiber. So you want to get rid of starch. So we gelatinize the starch to enhance digestion. That means we heat the sample a little bit so the starch gelatinizes. You add alpha amylase, break down the starch into maltodextrin and small triglycerides, oligosaccharides, and you digest the protein with a protease. You break down the proteins into amino acids so that everything is soluble. We add glucoamylase as well because you want to break down maltodextrin and oligosaccharides into glucose units that also will be in the soluble fraction of your sample. So now your amino acids, your proteins are amino acids, your starch are now glucose. So the starch components and the protein components are broken down into glucose and amino acids. And if we filter at this point, no, not filter yet. If we wash with ethanol at this point, I will precipitate the the soluble fiber. Okay. Otherwise, what will remain in the soluble components of your sample is the glucose, amino acids, and your pectin and hydrocolloids. So if I want to get total dietary fiber and I don't want to separate into soluble or insoluble, I can wash with ethanol. So the pectins and hydrocolloids will precipitate. Then I can filter at this point and separate my solubles from my insolubles, dry, correct for protein and ash, any residual protein or amino acids and ash that might remain with my fiber component. I need to determine how much there is and subtract the weight of that. So the final weight is only my total dietary fiber. This way, I can do it this way if I only want to get the total. If I want to know how much soluble and insoluble fiber I have, then before I precipitate with ethanol, at this point, I can separate my solubles from the residue at the point of after the hydrolysis with glucoamylase. So in this case, let me just find it. I don't go ahead with ethanol. I just from here, I filter and wash and end up with the insoluble residue and soluble permeates. So let's see what we can do with the insoluble residue. So the insoluble residue contains our insoluble fiber. So in this case, I get the residue, I wash it with water, ethanol, acetone to get rid of any anything other than my insoluble fiber. Dry, I take the weight. After I take the weight, I determine ash and protein in a sample. Then I subtract from my original weight, I subtract the amount of ash, I subtract the amount of protein, and after I subtract that, the final mass I get is the insoluble dietary fiber. What we usually do when we actually running the sample, we run it in duplicate, at least in duplicate. Rachel, correct me. And one of the duplicate sample we do protein on and the other one we do ash on. Is that correct? Yeah. And we have the weights of the sample so we can, because the ash, determine the ash, it's a destructible method. So we have to do two samples individually, one ash it and one do protein on it so that we can get the amount of ash and amount of protein and subtract from the weight we get of the total residue we have. Then we can determine how much dietary fiber we have that is specifically insoluble dietary fiber. We don't do this in the lab just because it's a lengthy procedure. It will never finish from beginning to end in one lab period. So that was the insoluble residue. Now the soluble that we bring here contains, so the filtrate contains amino acids, the sugars, glucose, and your soluble fibers. So I want to determine the amount of my soluble fiber. At this point, I can take that filtrate, precipitate with ethanol, and filter. Now, pectin and hemicellulose, pectin and hydrocolloids and gums will precipitate, and your sugars and amino acids will remain soluble and you throw them away. You take the precipitate, gets washed several times, and you dry it, you get the weight, and again, you determine protein content and ash content, and you subtract that from the weight, and you get the soluble fiber. If you do it that way, if you want to get the soluble fiber and the insoluble fiber, you'll get the amount of soluble fiber individually and the amount of insoluble fiber. When you add them together, you get total dietary fiber. So if you're only after total dietary fiber, you don't have to separate into residue and solubles. But if you want to know how much soluble you have and how much insoluble you have, then you do it that way, and then you add the final values to say, okay, I have this much total dietary fiber. Now, the integrated dietary fiber is another method where you look at originally small sugars and oligosaccharides, which this method does not account for. But I'm not going to go into the integrated dietary fiber one. So another method to actually determine the components of the soluble and insoluble dietary fiber, because you have, like I said, you have the pectin, you have the hydrocolloids, you have lignin, you have cellulose, hemicellulose. If you want to determine how much you have of each, you need to go and analyze the monomers of the different components. And to analyze the monomers, in this case, this method utilizes GCFID for all neutral sugars, and using calorimetric method to determine uronic acids, which are part of pectin. So the unit of pectin is galactouronic acid, is the monomer of pectin. So because it's an acid, in this case, it's not determined by GCFID. There is a specific method, that is calorimetric method, for it to be detected. Now, before we're able to detect neutral sugars, I need to also separate into my insoluble, soluble, and then break them into the different components. So the same process applies. So gelatinize the starch, hydrolyze the starch, break it down to glucose with glucoamylase, and break down the protein. Same thing. Then you get your insoluble, you get your soluble, and if you want to continue with the monomers, then you take this part, the remaining non-starch polysaccharides, that you hydrolyze with concentrated sulfuric acid to liberate free monosaccharides. The free monosaccharides at this point is then derivatized by acetylation to form stable and thermally stable and volatile compounds that you can measure with GCFI. Okay. Pectin analysis. So this is used especially when you have a food product that is predominantly containing pectin, and you want to determine how much pectin there is for quality purposes and labeling potential purposes. So let's say you have jams or jellies. So the main source of fiber in them is your pectin. So it will be measuring units of galactouronic acids, because the galactouronic acid, so here's the galactouronic acid. So this is, you have galactose as the sugar, and you have the acid group here, and sometimes it's methylated and sometimes not methylated. This will come back, I'll explain this more when I talk about enzymes later. But you have these galactouronic acid. The bond here is not broken because it's hard to hydrolyze by acid. So the way to determine the amount of galactouronic acids in this situation is you saponify with NOH. The saponification is going to deesterify. That's what you know with saponification, is a deesterification approach. So it's going to break the methyl group, and you'll end up having a carboxyl group here and carboxyl group here, and you have your pectins are in the galactouronic acid form that has negative charge here and negative charge here, and if you add calcium, you produce calcium pectate, which precipitates. So that precipitated calcium pectate is measured gravimetrically. So the last bit here that I have for you is for extra credit. So in this case, I give you data points. So you will be solving for soluble and insoluble dietary fiber components with this given to you. And you're going to determine soluble, insoluble, and total dietary fiber using this given. And following this, you want to get the average sample weight. These are the steps that you need to get basically to calculate those different soluble, insoluble, and total dietary fiber. So do this for an extra 5 points. I want each one of you to be able to do this. Since we're not doing this exercise in lab, at least I want you to understand it, do the calculations, and get extra credit for it. So Laura, Rachel, you will tell Laura to put that up for an extra credit due by, I would say, Monday, just to give them a little extra time. Monday, 5 p.m. Huh? She's on it. Okay, great. Thanks, Laura. All right. So that ends carbohydrate. I'll start fat characterization. Okay. Fat characterization is also one of my favorite topics. I do have a lot of favorite topics. I'm not going to tell you which ones are not my favorite topics, but this is one of my favorite topics. Okay. All right, let's see what you know or not know. Peroxide value is a measure used to detect advanced stages of lipid oxidation. So I don't know where you are with food chemistry. Have you covered fat, those of you that are in food chemistry? Yeah. What? What table? Oh, extra credit. So you have this in your slides. Huh? You got it? Okay. Okay. So you should have learned about lipid oxidation already. So maybe you remember if peroxide value is a detect advanced stages, and hexanal is an indication of advanced stage of oxidation. You might not know the third one, and which is the iodine value or iodine value, can be used to detect oxidation. Which ones you're sure is not correct? There's one for sure is not correct. And if you went over fat oxidation for chemistry, you should know that. Wrong. B is wrong. A is wrong. A is wrong. So peroxide value determine peroxides, and peroxides are the primary oxidation products. So when unsaturated fat oxidizes, your first reaction products are peroxides. So as we go to advanced stages of oxidation, then you can get hexanal as one of the products, secondary products of oxidation, secondary or advanced stages. Malonylaldehydes or aldehydes in general are secondary stage or advanced stage oxidation products. So iodine value is actually, it measures degree of unsaturation of oil. So we will learn about it and about that method. Because it measures degree of unsaturation, which is a physical characteristic of the different fatty acids, that make up your oil. So different oils coming from different sources have a different degree of unsaturation. So the more double bonds you have, the less degree of saturation that you have in your fatty acids. So the more double bonds you have, the higher is your iodine value. And we'll learn about the chemistry of this method. Maybe not today, next time. So because oxidation saturates double bond, because oxidation attacks double bond, we can also see a reduction of iodine value in an oxidized oil. So if our oil is oxidized, the iodine value, we usually, for identification purposes, different oils, there are tables for iodine value, there are tables for saponification value, there's tables for refractive index, and so on. So the iodine value of the reference oil will be higher than the iodine value of an oxidized. So what's the answer to this one is B and C. So B and C are correct. A is incorrect. So saponification value is often measured to detect level of fatty acid saturation. No. So this is false. We'll learn about saponification value, and once you learn about saponification value and iodine value and peroxide value and the rest of the analyses, you will be able to be asked this question and to be able to answer it as false. Okay, so we're going to learn about all of these different assays. But first, like always, why do we care? What is the importance of fat characterization? With fat characterization, I can tell you, we're going to cover what is the fat made up of, saturated, unsaturated, cholesterol, trans fat. So we are going to learn about the oxidation, different oxidation products, and how we're going to measure them. So by listening to this, what's the importance of fat characterization? Chrissy? Shelf life and stability. That's a big one. Because when the more unsaturated fats you have, the more prone the oil is or the fat is to oxidation. So it's very important to characterize the fat components and determine its shelf life. One. Sam? That's good. We need to determine, because we want to determine shelf life, we want to determine, okay, well, this is highly polyunsaturated fat. We need to make sure they don't have oxygen permeability. Good. What else? Abby, nutrition label, exactly. Because in nutrition labeling, you see total fat, but you also see saturated fat and you see trans fat. So let's reveal this for a little bit. So yeah, the saturated fat, trans fat is part of the nutritional labeling. And so it's not only determining total fat, we also want to determine what different components do we have. And we also have cholesterol, not to forget that as well. It's part of the lipid component of your food. All right, shelf life stability. Palatability and sensory effect. So for example, you get the total solid fat index is called, and it's very important, that index, for how much you can spread the fat. Okay, and let's say I cannot believe it's butter, right? So this is based on vegetable oil that has been hydrogenated and also mixed with polyunsaturated oil, so that you get that consistency similar to butter, but it's not very hard as butter because it still can be spreadable. Safety, secondary oxidation product can be a safety concern, such as cholesterol oxide and malonylaldehyde can be carcinogenic. So it's very important to analyze from that perspective. Now, processing is important. We're going to talk about processing here in a minute, but so we covered nutrition label, shelf life stability. So other than oxidative stability, I didn't talk yet about hydrolytic rancidity. So there is oxidation of your fat, and there's also the breakdown of the fat. So if you have endogenous lipase, let's say in flour samples, whether it's oat, mostly oat because you have high percentage of lipase and lipoxygenase enzyme, but also in wheat flour, it is also an important parameter for shelf life of the flour. So lipase, endogenous lipase, is going to break down your lipids into fatty acids. Fatty acids have off flavors. Okay? It's not a desired flavor that you would get. And not only that, free fatty acids are more prone to oxidation than triglycerides, than fatty acids within a triglyceride as an esters. So free fatty acids are more prone to oxidative rancidity. So you end up having hydrolytic rancidity that will potentially increase oxidative rancidity potential. The other thing here that I have on here is sometimes you add components that simulate lipids, but they don't give you the calories, such as olestra. So we need to make measurements to differentiate how much actual fat we have versus a simulate of lipid. Okay, now processing is really important, especially for bulk oils. Processing effect for bulk oils or oils for frying, where you have sometimes in when they produce when they produce fried snacks, they reuse the oil quite a bit. So things happen when you reuse the oil. And we'll talk about that in a minute. But also when you process the oil, so you crush your seeds. So this is a diagram that shows you the processing of production of the oil. So you get your seeds, you clean them, you dehull them, you crush them, you get your oil. The first pressed oil, we call it crude oil. Say this is very common if you go to supermarket to buy olive oil, you see extra virgin olive oil, non-refined, so as is. So there is the crude oil, and then you have the refinement of the oil. In the crude oil, you have a high percentage of free fatty acids. So you refine the oil to get rid of the free fatty acids. So in refinement of the oil, you use an alkali treatment. So let's say you add NaOH. The NaOH reacts with fatty acids, gives you soap and water. And that soap and water you spin, separate the soap and water from your oil. So you refine it that way. So basically, what you're doing is you're getting rid of the free fatty acid that gives you this distinct flavor or that has the potential for oxidation. So that's your refined oil. So if you want to determine how well the oil was refined, the adequacy of refinement, you can measure total free fatty acids. So that is another measurement you do for oil and fat characterization. So you measure total free fatty acid, and you can determine as a producer of oil if your refining step was done correctly. Okay, that's good. So another thing is hydrogenation. When we are producing solid fat from plant or vegetable source oil, you hydrogenate. That means you saturate double bonds. So if you wanted to hydrogenate, you want to make sure that you complete the hydrogenation. Incomplete hydrogenation can result in trans fat. So your cis formation of fatty acid will be converted to trans in your triglycerides. So you convert cis fat to trans fat, and that is not good for cardiovascular health. So you measure extent of hydrogenation, and if it's incomplete, there's a potential of production of trans fat, which you want to measure as well. Deep frying. Okay, that's when we fry with oil, potato chips, for example, or potato fries. So it has water, right? Your potato is rich in water. You put that potato in the oil. So you have water, you have heat. You cause hydrolysis of triglycerides. So you start forming free fatty acids. So then the quality of the oil will deteriorate. You'll get oxidation as a result of that. So deep frying multiple times with the same oil can result in the hydrolysis of the oil, production of free fatty acid, oxidation, and potentially production of toxic components for advanced stages of and just every time I teach this lecture, I remember that I need to change my oil in my fryer. It's like, how many times did I use my oil? Yeah, so do change your oil. Do not reuse it because of the fact that you get toxic compounds with more uses of your frying oil. Let's see what we didn't cover here. We talked a little bit about mouthfeel and taste. Definitely taste is impacted by rancidity, oxidative rancidity, hydrolytic rancidity, and the solid fat index as well. So, which is a very important index to determine the spreadability of the fat. When you put it in your mouth, how quickly you feel that melting sensation, the mouth feel, smoothness of that lipid component. And we talked about safety as well. Oh, one thing I didn't talk about is winterizing. And we will have tests to determine the effectiveness of winterizing. Does anybody know what winterizing is of oil? It's part of the process of refining the oil. So you have refining, you have bleaching, filtering, so bleaching to remove any colors. And then one step somewhere here, there is winterizing and deodorizing. So winterizing, does anybody know? Let's see. All right. Sometimes you have waxes in your lipid components, and let's say you put your oil or the dressing, let's say if you have dressing, you have oil in your dressing. When you put them in the fridge, they get cloudy. It's not desirable for consumer acceptance. So the winterizing process is they chill the oil. So from the word winterizing, so making it cold. So they chill the oil, and then your waxy material precipitate, and you get clear oil, and they separate that waxy material from your oil. So to determine again the effectiveness of winterizing, they take a sample of oil, they cool it at specific temperature and see if any cloudiness or precipitation occurs. If none, that means the winterizing process in the plant was good enough. Okay, I think here it's a good stopping point before I go into analytical methods. This would be a question that I'll ask on Friday to see how much you remember. But I'll stop here. We have 3 minutes, but it's not worth starting here. Okay, see you on Friday.
Hey, Pam.
You have a question, Jean? Just a second. I'm going to stop recording here.